behavior. So in time, the input is 0, 0, the output is 0. So these two things are just the same information represented in different ways. And especially in the lab, you're basically going to see this representation more often in simulators. Which is why it's good to be familiar with that. The AND gate is the next basic gate. So this gate, the output is 1 when A and B are 1. The NOT gate inverts the output, so the output is just the inverse of the input. So here's an example of how a larger schematic is connected together based on a few simple units. So if you need to find the output, if you have a large schematic with a bunch of stuff and you can add more gates to it, you can have another AND gate connected somewhere. All you do, and you can have, as I said before, you can have multiple inputs, so we call this X. So we can go through the whole diagram with each possible input. So for example, 0, 0 is an input here, you just put 0, 0. So the output of the AND gate based on the truth table is 0. The 0 goes up here, 0 goes down here, the NOT gate inverts it to 1, you get 1 there, and 1 there. So then the output Y equals 1, X equals 1, so then you fill this column. That's 0, sorry. Because this is an AND gate, not NOR gate. And you can just keep going for every possibility. If you operate a moving function of a diagram, which we'll do later to reduce the diagram, simplify it, avoid having to go through every single state. So as I had shown before, the moving operators, the AND is this dot, or is this plus, and not we show with a line above it. So you just, starting with say A and B, you can say this point here is A and B. If you want to consider other points, so A and B, and is equal to C. So the output here is not C, it's equal to not A, B. This point is the same as C or A and B. If I'm going to OR gate, and as I said before, this point C, which is the same as A and B, the output here is C or with C naught, and simply substitute the values of the attempt. So this example, I can rectify the Boolean output. Likewise, if you're given just a function, you can derive a schematic diagram. So if you're given just this, you can sort of do the opposite to get to that state. So you can just start at one point, you can say, okay, I have Y equals A and B, so you've got the AND gate, and you say this is equivalent to that gate, you just work your whole diagram. So you can do examples of that, and as I said before, from the course website, there's examples of previous years' assignments, you can do a bunch of examples of this, course notes have examples of this, so there's no shortage if you want to do a few check yourself. You'll see little circles in the schematic diagram, these just mean the simplest way to think of it. So we can take an AND gate, add a inverted NOT gate here, and this circle is what we're looking at, so if we just run that, that's a NOT and an AND gate. In a similar way, we can have a NOT OR gate, which is a NOR gate. The advantage of the NOT AND and the NOT OR and NOR gate are that you can actually perform all basic operations just using an AND gate, and just OR just using an OR gate is one of those gates. So the simplest example, if we connect the inputs together, will form a NOT gate because the AND are always the same, and the output is the opposite of that, because it's an AND function. So in a similar way, you can create other gates like an OR gate. So if you look at the truth table, you see the output is 0 of the OR gate, only when both inputs are 0, 0. For the AND gate, the output is 0, only when both inputs are 1. So what you can see is that you just invert inputs to this gate here, and you end up with the OR gate. So that's what we want to see, and as I said before, we can generate this by using AND gates as inverters, and then so using 3 AND gates to create an OR gate. Why we care so secret with this is that you can have a system where you just have AND gates, just have millions of AND gates or millions of OR gates, and just by how you interconnect them, you can create huge devices. So here I created an AND gate from this matrix with AND gates. So the same AND gates could have been connected up to create that OR gate example I had. So the exact same arrangement and just adjusting how it's connected, we create OR gates or AND gate. So the final basic gate we consider the exclusive OR, or the XOR gate. And the XOR gate is what we'll call difference gate. We'll use it in binary adders, subtractors as well, is where it's important. And the output, you can see, is 1 when only one of the inputs is 1, but not both. So you might call it a difference gate as well, because it's providing you a high level when the output is there, but it's low if they're the same. And you can implement it from other basic gates as before. If you add an inverter on the output, we get the exclusive NOR or XNOR gate, and it provides the opposite functionality. So the output is high when the inputs are the same. So it's very low. So yeah, that's all the schematics of the basic gates that we'll consider in this course. When you physically build them, I share with you an example of switches, and you can consider other gates using switches. The AND gate is just 2 switches in series. The NOT gate, you can consider the switch with a resistor, such that when the switch is open, the output goes high because it's connected through the resistor. When the switch is low, the output forces to 0. So this is how you build an inverter. We don't really forget, we don't have switches here, we don't have switches physically in there. What we use are transistors, the particular field are transistors like that. And they are electronic switch basically, if you consider when the input is high, the switch is closed. And we'll have complementary versions of the switches such that there's a game with a little circle, indicating that when the input is high, that switch is open. So if we put a 1 here, this is what we get rid of the resistor in these circuits. So if we put a 1 here, that means this switch is in 1 here. This switch is closed, and this switch is open, which means the output goes to the ground. And we'll call that complementary metal oxide semiconductor, because it's gives 2 types, the complementary positive and negative, basically, switch types. And you can build all basic gates with these sort of electronic switches. So, again, here's an example of an AND gate. And if you want an AND gate, we just add an inverter on the end. A NOR gate, again, if you want an inverter, just add, if you want an AND gate, an OR gate, add an inverter on the end, sorry. There's several different types of logic family, so everything we'll be dealing with will more or less fall into this CMOS category. This is what most electronics today is basically CMOS. Some of the older technologies, when you don't use it all, like resistor transistor logic or diode transistor logic, we probably run into TTL transistor logic, which is one of some of the first really popular logic gates in logic families. And why power, you got tons of power for the environment, but you want high speed, so you make that trade-off. So then we talk a bit about number systems. Decimal is the one we all know, where you have 1, 2, 3, etc., where each digit has a certain value. So this is equal to 3, equal to 20. In binary, instead of having that system, what we use is, what we have is that each value has this binary base 2 number system. So rather than being worth 1, 10, 100, 1,000, it's worth 1, 2, 4, 8, 16, 32, 64, 128. So if you want to convert a number, you can basically just, in a standard fashion how decimal works, add up the equivalent value of that digit. Because we only have to deal with 1 and 0, it's even easier. So the number is either add this or you don't. So in this example, I'm converting from binary to decimal. I figure out the value for each place here and added it up. In the opposite way, you can simply consider the value of the number and work backwards effectively. So starting with, for example, 216, you can find the highest value that it will fit within. So the value of this digit is 256. So obviously that's no use to us because 256 is higher than 215. So that means there'll be a 0 there, and just ignore that. So we put 1 in the 128th position, and then we subtract 128 from 216 to get 88. So the rest of these have to add up to 88 now. So then we go 88 minus 64 is 24. So this is greater than 0, so we'll put 1 here. And the rest of these then add up to 24. So the next position is worth 32. 24 minus 32 is smaller than 0, so when you put a 0 here, you can't use it. So we try again. 24 minus 16 is 8, greater than 0, you put 1 here. So the rest of these now have to add up to 8, which comes from there. Finally, 8 minus 8 is 0, that's okay. We can have it 0, it can't be lower, so we put 1 there. And the rest of these then have to add up to 0. So obviously we just put 0 in the remaining position, so you can go through it, 0 minus 4, below, etc., etc. We'll use subscript to indicate the base of the number. So base 2, we'll use a 10 subscript 2 means it's binary 1, 0, not decimal 10. So in this case, binary 1, 0 is equal to 2 in decimal, base 10. You may also see a subscript D indicate decimal, subscript D indicate binary. Check your conversions if you want to use Windows Calculator. If you have a calculator that does it, that's fine. You'll also see we'll use in this class hexadecimal and octal number systems. So hexadecimal means base 16, and octal is base 8, unsurprisingly. Why these number systems are useful is that you can map them directly. So in binary, for example, if you have these 4 digits, and they're 1, 0, 0, 0, it's equivalent to hexadecimal 8, or 1111 is equivalent, for example, to hexadecimal F. So if you have a whole bunch of digits together, you can just break them directly. So you just convert each group of 4 bits into the hexadecimal equivalent using that table. So this way you can convert back and forth. When we're talking about binary, it's worth noting that we give a name to each group of 4 bits, and that's the nibble. And 8 bits, we'll call it byte. So 2 nibbles make a byte. I guess quick joke, but I don't know. That's the actual name for it. With octal, instead of splitting in 4, we split it into bits of 3. But again, you're doing the same sort of process where you just take 3 bits, convert them to the octal, write it all together. So the advantage of this is that you can easily write down if you have an address or something. You can write down X number pretty easily, email someone, they can convert it back if needed. And when you're programming and everything like that, you almost always use hexadecimal for this reason, if it has to deal with the bits. BCD, binary coded decimal, is a number system where rather than converting to decimal entirely, you simply convert parts of the number. So if you say you have the number 273, and you want to convert it to BCD, what this means is that each digit of the decimal number just gets converted to a group of 4 binary bits. So 3 becomes 0, 1, 0, 0, 1, 1, 7 becomes 0, 1, 1, and 2, 0, 0, 1, 0. So it's somewhat wasteful because we're only using from 0 to 9. So if it's 299, it becomes 0, 0, 1, 0. This 9 becomes 1, 0, 0, 1, and this 9 becomes 1, 0, 0, 1. So in BCD, the 4 bits map just to a binary bit. So you can't see anything, for example, if you had a BCD number, this is invalid because this is equal to 9. But this is too big that can't map to a bit, because if you look at the table, you'll see 110 is equivalent to 14 in decimal, which makes no sense. So that's not possible. So that's why BCD is wasteful, and it's used a little bit. We'll probably use it in a few labs, so that's about it. So let's actually review all that class. We'll take a 5-minute break before starting the next stuff. If you want to get lunch or something. We'll give you an example of adding a binary. If we have 2 numbers, say 1, 0, 1, 1, 0, 0, 1, 0, 1, 0. In a similar way to adding a decimal, you just add each column in sequence. And in binary, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 1 is 0 with the carry of 1. So you can just use those to complete the whole sequence. So 0 plus 0 is 0, 1 plus 1 is 0 with carry of 1, and just like in decimal, with carry, you just add it on. So 1 plus 1 is again 0 with carry of 1. 1 plus 1 is 1 or 0, carry 1, 1 plus 1 is 0, and then your carry 1. So as you can see, it's the exact same sequence of events as you would with normal numbers. So normally, when we subtract, it's also very similar. So if I subtract in binary, example here. Or actually, before starting subtracting in binary, I'll just refresh your memory. This may have been a long time. Subtracting in decimal, in a similar way, we'll be using the idea of borrows. So 3 minus 7 is too big. You'll borrow 1 from there and make this 13. So you have to remember the 1 in this case means 10 to the power 1. We're dealing with decimal here, base 10. So it then becomes 13 minus 7 instead of 3 minus 7. So with this, then you can complete that. Again, you get 1 minus 6, you'll borrow. 0, 0, or say 1 minus 0 equals 1, 1 minus 1 equals 0, and 0 minus 1, this is where you use the Borrow. So you're, because obviously you can't just do that without getting a negative result. So in this case, 0 minus 1, we'll borrow from here and put 1 there. So when you're doing with binary subtraction, the thing you have to remember is that with decimal, this would equal to 10 to the 1. Because it's binary, it's effectively equal to 2. Or you can look at this 1, 0, and say binary 1, 0 equals 2, because that's an easier way to remember it. So then you have 2 minus 1, gives you 1. So that's how we deal with the binary Borrow operation. So then we're using the Borrow there. So then we just keep going as before, 0 minus 0, 0, 1 minus 1 is 0, and again 0 minus 1, we use the Borrow from this digit. And if this was 0, 2 minus 1 is 1, 2 minus 0 is 0. So you go. So that's simple examples of subtracting in binary. When we do this, we'll also have this issue of positive and negative numbers. So obviously you can do anything. You can go 9 plus minus 2, or 9, negative 9 minus negative 3, and there's also a combination here. So we need a way to represent negative numbers in binary. Everything we've been talking about so far has been the case of positive numbers. So when I have the binary number, I'm saying that this is equal to 2 to the 0, this is equal to 2 to the 1, this is equal to 2 to the 2. So there's no way to represent something like 0 here or there. So one easy way that you might first think about doing that is if we have a wheel here, and have all the binary numbers written down from 0 to what would be 15, and we'll use one of the bits to indicate the sign. So we'll use signed numbers here. And say I'm going to make this bit here. You can assign it. If that is 0, the number is positive. If that is 1, the number is negative. And so if we do that, you can just go through and say, okay, this would be 0, this would be plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. And you get here, we have 0, 0, 0, which is 0. You have to go 1, so we have minus 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, and minus 7. So at first it seems like it's a pretty easy way to do it, because we just use one bit to be positive or negative. That's simple enough. But there's some oddities here. First of all, you'll notice there's positive and negative 0. So doesn't make a lot of sense. The second thing is that if I do an example, so I'm using this representation, and let's just use some normal binary math. And it doesn't make any sense at all. So if I have minus 5, which I said was represented by this, signed it, and then 5, and I add positive 1, this is an expected result somehow minus 4, but if you just add them together using regular addition, you get minus 6, so that can be right. Similarly, if you just add 2 negatives, which you say, well, okay, maybe there's something weird because 1 minus 1 positive, but even if you add 2 negatives, it doesn't even work out as you expect it to. So what this means is that it's not very efficient in computer, because you have to deal with all these different cases. You have to have one addition circuit that works if both numbers are positive. So you'll have one circuit there, you'll have another circuit working if both numbers are negative. Such as this. Obviously, we can't use the same addition we're using here, and then you have to deal with cases where one's negative and one's positive. So it's just not a good way of doing it. And to sort of get us into what we used, you may have a question of where did 0 come from. Here's 2 zeros. Why do we have 1 0, 1 have 2, 1 have 0? For getting the zeros, there's pretty interesting about all the zeros where it came from. But one of the real first in history, first kind of written records of this and with a lot of confidence to it, was in India in 628 AD. And here are many of the rules that you would know as being elementary to this, but originally these were not so obvious. So here, sum of 0 and a negative number is negative. So 0, when you add the negative number, you expect it to be negative. 0 and a positive number is positive. 0 plus 0, you expect to be 0. So again, this is an issue because if you add these two up, you'll get positive 0, negative 0, and then negative 0. So why don't we see which one is important here? And this final point he's brought out is the critical one that really underlies what we're going to do next. The sum of a positive and a negative is their difference. So rather than doing subtraction, we're just going to add negatives. And there's a reason we'll do that that'll sort of become apparent in a bit. To really see how it works, we have to talk about complementary numbers. And the complementary numbers are numbers that are nice here or anything. It's a mathematical term, and we'll talk about the radix, the diminished radix complement first. And this is, say, in decimal. So decimal, the radix is equal to 10, base 10. So the diminished radix is just 10 minus 1. So the radix minus 1. So for decimal, the diminished radix complement is 9. So when we want to use the diminished radix complement type math, what this means is we want to add, we want to do subtraction with addition. So say I have an example here. Say I have 543, and I want to subtract 273. And where some of the time came out is that sort of down people were not as strong in math. Doing this with subtraction is a lot more boring, and there's a lot more chance for error. So especially with numbers from younger persons want to do this quickly, we wouldn't know the right way of doing it. People are pretty good at the idea of adding and carrying, but choose more intuitive. Choose when you're just going through it. So we use the diminished radix complement to do the subtraction. So to do it, the first step is we get the complement, so the 9's complement is diminished radius of that negative number. So the number that we're subtracting here. When we say we're going to add, what we want to do is add this. So we get the 9's complement of it. So to get the 9's complement, all you do is subtract 9 from each digit. So we'll go 9, 9, 9, and we'll subtract out 273. And what you're left with is 726. So 9 minus 3, 6, 9 minus 7, 2, 9 minus 2 is 7. So this is the 9's complement of 273, negative 273. Or yeah, 9 complement of 273, so a negative. So the next step is then to add to 543 this 9 complement, or add to it the 9 complement here. So we'll go 543 plus 726. And we'll just do this as a regular addition. So the result is 6 plus 3 is 9, 4 plus 2 is 6, and then 5 plus 7 is 12. There's a little bit of a trick when we're using the diminished radius complement, the 9 complement, is that we have to take this 1 down and add it here, and then add it in. So then we get 269 plus 1. So if there's something that's out there, you have to add it back in to the regular digit. So that equals 270, which is the same as if we just did this subtraction in our original case. So without using Boros, you can use the diminished radius complement, the 9 complement, to do subtraction. So we can use this with binary systems. So binary base 2, the diminished radius complement, will be the 1's complement. But there's an even easier way to some degree, and that is that remember I said we had this issue here where we have to get this 1 and take it over. So we can use the radius complement. So for decimal, this would be the 10's complement, say decimal, equal. And again, for binary, we'll have what's called the 2's complement. So I'll show you the example for 10's first, and then we'll have a few more examples. So for the 10's complement, instead of subtracting 9 from each number, we subtract, basically in this example, 1,000, so 10 to the power number of digits from the whole thing. So I have the example of 543 minus 273. So to do this, we will get the 10's complement of this. So the 10's complement is 10 to the power 3 minus 273. So equals 1,000 minus 273. So the disadvantage of this system is that when we initially do this, you'll notice you do have 4, which seems like you're kind of avoiding all. But here it's slightly simpler. And obviously what you're going to end up with here is that you'll be borrowing from all of these to get 9, 9, 10. So you'll notice it's basically, the result here, the 10's complement or the radius complement is the diminished radius complement plus 1, because we have 10 here instead of 9. So this will work out to 727. So before, I had 726, here it's 727. So in the same way, we can then just use addition to get this answer. So we can go 543 plus 727, and this will give us 1270. So with radius complement now, we can say more if it doesn't carry. Because when we added this with 5 plus 7, we don't 12. So it's greater than 10, so we have a carry of 1. But there's all zeros here, so we just write it down. So if we ignore that, and the answer you get is 270. And the other thing when we're using radius complement is that we have a case where this seems kind of nice and significant here because that large number minus small number, and the result has been understanded. But we can do this with a small number minus a large number, and what we'll end up with is that the result is in the radius complement format. So, for example, if I do, I'll just do the opposite, 726, let's read that up to whatever you and 273 start with that, minus 543. So in the same fashion, we'll take the 10's complement of this number. So we'll go 1,000 minus 543. In the same fashion, we'll borrow 1 that we got here and 10 there. So we want to get the 10's complement, so 10 minus 3, 7. So what we're going to is the 10's complement of this number. So then again, the next step is to add the 10's complement to the original, and that's just over 3 the subtraction. So 1 of 10 is so we're getting over 730 here. So we know the answer is supposed to be negative because 273 minus 543 here, that's the negative number. So when we do addition, we keep track of that. That should be negative, and we convert this number back using the same type of subtraction. And we have the result, so I'm going to choose the so it gives us minus 270, and again, we know it should be negative, so negative 270. And just add that in because we know the result here is in 10's complement format. So then you convert to decimal. So then you subtraction without doing any serious subtraction, most of it in addition format. So for decimal, they're not seen as important, but yeah. Yeah, so it's just whatever time that's the point they will. Yeah, I can't guarantee because I haven't checked every time, but they should. Yeah. So when we talk about the radius complement, here we're talking about the 10's complement. So binary, we want to send the 2's complement. So the 2's complement is the form we'll use to do the same sort of subtraction. So the 2's complement is the exact same idea. We want to do subtraction, but rather than subtracting and using the form, we'll just add. The advantage of this is not going to make life a little easier. Like when we're designing a computer, we just need to add block. If you do it in this format, then you can generate the 2's complement efficiently. You can just add everything. Just convert everything into the proper format before and convert it to the add block as needed. As it works out, that is actually a lot easier to do the conversion. That's to decide how you logic convert the 2's complement, and then one adder is smaller than having the logic to adder and subtractor. So there's a few ways to form the 2's complement. So the fastest way forward is just to think, okay, well, all I do is convert each single bit. See some of the rate inverse. So 0 becomes 1, 1 becomes 0. So this is, in general, this is the only number. You can this is just the setup used. So then you add 1 to it, and the result is in the 2 combo. So this is 1s, and this will be 2s. So here is the binary addition, 1 plus 1, 0, carry 1, 1 plus 1 is 0, carry 1, and then the rest of them are just written. And so that's necessary to do combos. Binary numbers. So you notice, for example, your science graph, to the addition, you're going to do combos of this negative number. So when you put that as 8, it's just the number, you'll minus A3 or A3 to binary, and you get whatever you get. And then you just take a method to get the 2 combos. And if, so we can this here, and for example, if you have a grade B 15-bit do comment, the one thing that's important to remember is that you have in fact extra 0 bits here. The may or may not be written in this case, so I'm going to written 10 bits. If I have a grade 16-bit do comment, you don't remember these zeros will actually have been inverted then. So you'll have to then append and even 1s, so they have the extra 1s. So that's just we're going to get slide 4. You know, put these slides online. And the second way that we can do it is, actually more about the second way, there's a bit of a reason we're using recovered bits. We have a bit that has the smallest size, this is bit number 1. And this bit, which when we are raising out beyond the right-hand side here, we'll call it the least significant bit. Or LSB. But then it has I value assigned with it. So this bit has value 148 because it's a 7-bit number. It's 8 bits, 256, etc. And this one, we're calling the MSB for most significant bit. When we're using it, that'll be on the left-hand side. And that's fairly common to have this notation where the least significant bit is the right, most is the left. It's not guaranteed for all of your systems, depends which way you're representing stuff though. For this class, you can continue in that direction. So, when you want to talk about 2 columns, it's a bit of a shortcut. You can do one condition, and that is that you, starting at the least significant bit, so starting here, you just start inverting bits and you break it down in inverted form until you get your first 1. So I think this is 1. I think this is 1. And the first 1, we write, I think we're going to lose check. Yeah, so the 1 we write as is, I should get it backwards. Yeah, you can count them as is, you count those as is, and the rest you invert. So we count the first, get up to that first 1, including the first 1 as is, and then you invert the rest. And that's what you count them for. It's a little bit faster if you remember to do properly. It's not just invert them and add 1. I think that's more reliable. So that's a bit of a fast way. So if you written down. So a few more examples of that I'll just show you. So if we use the fast method, we would just copy this as is, copy 0, the first 1, we'll copy as is, and the rest of them, we have invert. So 0, 1, 0, 1, 0, 1, 1, 0, 0.